Hey everyone, buckle up because today we're going to dive into the heart of what makes your games look incredible, NVIDIA's Turing architecture.
We're talking mind-blowing graphics,
AI, that seems like magic.
all thanks to this revolutionary piece of tech.
Now, I know staring at a white paper can feel like trying to read another language.
It's definitely dense.
So we're here to break it down, no jargon allowed.
And what's really amazing is how NVIDIA took something that started with gaming, the GPU,
Right.
and turned it into this engine that's powering so much of our digital world.
Yeah.
We're talking everything from the realistic graphics you see in movies
Wow.
to the AI that seems to be learning new tricks every day.
It's like they said, what if we could take the same tech that renders epic explosions and use it to, I don't know,
Right.
predict the weather or something? And the crazy part is,
They kind of can.
they kind of can.
And Turing was a huge leap forward in making that happen. NVIDIA themselves called it the biggest leap in over a decade,
Wow.
which in the world of tech is like saying you've discovered a new element.
Yeah.
It's a big deal.
Okay, so biggest leap has got to mean some serious horsepower under the hood.
Oh, absolutely. We're talking 18.6 billion,
Billion.
with a B, billion transistors, the tiny switches that make all the calculations happen.
Oh, wow.
Imagine trying to count all the grains of sand on a beach, and that's the level of complexity crammed onto a chip smaller than a postage stamp.
It's mind-boggling.
It is.
And all of that power translates into the stunning visuals we see on our screens.
Right.
But before we get lost in the billions, how do we even measure something like that? I keep hearing terms like TFL OPS thrown around.
So think of TFLOPS as calculations per second, but on a scale you can barely imagine, we're talking trillions of them. It's the raw processing power that lets your GPU keep up with the demands of today's games.
Okay.
And with Turing, they introduced GigaRaySec and Tensor TFLOPS,
Okay.
which basically measure how well the GPU handles ray tracing. That's for super realistic lighting and reflections, and AI, which is used for everything from making your games look sharper to, well, potentially predicting the weather one day. Who knows?
So it's like comparing the horsepower of a sports car to,
Yeah,
I don't know, a spaceship.
something like that.
These metrics are how the pros figure out what a GPU can really handle.
Exactly. Now, to really understand how Turing achieves all of this, we need to crack it open and look at the engine, starting with the streaming multiprocessors, or SMs.
Okay, hit me with your best car analogy because I need a way to wrap my head around this.
All right. So think of the GPU as a powerful engine, and those SMs, they're the cylinders firing away to deliver all that horsepower.
So more cylinders, more power, got it.
Basically, yeah,
But Turing's SMs are something special, right?
they are. They redesigned the SM for maximum efficiency, resulting in a 50% performance boost
Wow.
per CDA core compared to the previous generation.
Okay.
And CDE cores are basically the tiny workhorses inside each SM doing the actual calculations.
That's a huge GE jump. It's like they figured out how to get 50% more horsepower out of each cylinder.
Right.
What's the secret sauce?
Two big changes.
Okay.
First, they added an independent integer data path. Imagine you have a highway full of cars, and suddenly a whole new lane opens up just for trucks.
I like it.
Everything flows smoother and faster.
So less digital traffic jams for all the data zooming around inside the GPU.
Exactly.
Makes sense. What's the second big change?
They completely overhauled the memory system, creating what they call unified memory.
Okay.
It's like taking a messy workshop and organizing it so everything has its place.
I like it.
Now the GPU can access the information it needs much faster,
Right.
which, as you can imagine, speeds up everything it does.
So it's not just about brute force processing power, it's also about working smarter and more efficiently.
You got it.
And that seems to be a recurring theme with Turing.
It is.
And speaking of working smarter, Turing also introduces these things called tensor cores, which are specifically designed for the complex math behind AI.
Yes.
Hold on, AI right inside the GPU.
It's pretty amazing.
Tell me more about these tensor cores.
Imagine having a coprocessor in your GPU
Okay.
whose only job
Right.
is to make sure AI runs blazingly fast.
Wow.
That's what tensor cores are all about. They're built for the kind of heavy-duty number crunching that powers those almost magical AI capabilities we keep hearing about.
Okay, so we've gone from souped-up engines, those SMs,
Right.
to dedicated AI muscle with these tensor cores.
Exactly.
What makes Turing's tensor cores different? Did NVIDIA give them a turbo boost too?
It's more like they gave them a whole toolbox.
Mm-hmm.
Turing introduces new precision modes called INT8 and INT4.
Okay.
Think of it like this. You wouldn't use a sledgehammer to hang a picture frame.
Right.
You'd use a smaller, more precise tool.
Right. Yeah.
These new modes let the tensor cores work faster on tasks where you don't need absolute precision, making AI processing even more efficient.
Okay. So it's all about using the right tool for the right job, even at the AI level.
Exactly.
But how does this actually affect, us regular folks?
Sure.
Are we talking about AI playing my games for me anytime soon?
Not quite yet, but this AI power is already making its way into the games you play every day,
Okay.
especially when it comes to visuals.
Okay.
One of the most exciting examples is deep learning supersampling, or DLSS for short.
Oh, yeah, I've heard of that. It's like AI upscaling magic that makes games look even better without needing a crazy powerful PC.
That's the one.
Okay.
Ever notice those jagged edges or aliasing in games, especially on objects in the distance?
Yeah.
Getting rid of those while keeping the game running smoothly is really difficult. DLSS is like having an AI clean up those edges, making your game look like it's running at higher resolution without sacrificing performance.
Okay, now that's something I can get behind.
Right.
Sharper visuals, smoother gameplay. It's like the best of both worlds.
It is.
But we haven't even touched on what's arguably Turing's biggest claim to fame. Ray tracing.
I guess ray tracing.
Kind of a big deal.
Right, it's a big deal. For years, it was the holy grail of computer graphics.
Really?
The key to unlocking truly realistic lighting and reflections in games. But before Turing, it was just too computationally demanding, too expensive to pull off in real time.
So for those of us who aren't graphics wizards,
Sure.
explain ray tracing like you're talking to, well, me. What's the big deal?
Imagine you're playing billiards, right? You hit the cue ball, and it bounces around the table, hitting the rails and the other balls.
Okay.
Ray tracing is kind of similar, but instead of a cue ball, we're talking about light rays bouncing around a virtual scene. The way those rays bounce off surfaces, refract through objects, that's what creates those subtle lighting effects that make a scene look incredibly lifelike.
Okay, I'm picturing it now, and
Yeah.
it sounds amazing.
It's really cool.
But you said it was too computationally expensive before Turing.
It was.
What changed?
Turing brought a secret weapon to the table. Dedicated hardware units called RT cores.
RT cores.
These cores are like mini supercomputers designed specifically to accelerate those complex ray tracing calculations. It's like giving the GPU a turbo boost just for making those beautiful realistic lighting effects happen.
So it's not just about throwing more raw power at the problem. It's about designing specialized hardware that can handle those calculations with incredible efficiency.
Precisely. And the result is what are called a hybrid rendering approach.
Oh.
Turing combines traditional rendering methods, which are fast, but not as realistic,
Right.
with ray tracing for specific effects where realism really shines. It's like taking the best of both worlds and blending them seamlessly.
It sounds like Turing is the ultimate multitasker.
Right.
But the innovation doesn't stop there, right? There's also this thing called NVIDIA NGX, which sounds like a whole other bag of AI-powered tricks.
It is.
Okay.
NGX is like NVIDIA's secret sauce, a suite of tools that leverage AI to enhance games in ways we never thought possible.
Right.
And you're right, it's not just about DLSS, although that's definitely a star player.
Okay. So what else can NGX do?
So,
Give me the highlights.
have you ever taken a picture and wished you could magically remove that annoying lamppost in the background?
More times than I can count.
Well, NGX has you covered with in-painting. It uses AI to intelligently remove unwanted objects from images, making it look like they were never there.
That's incredible. It's like having a digital eraser powered by AI. What else?
Then there's AI slow-mo,
Okay.
which generates super smooth slow-motion footage. You know how regular slow-mo often looks choppy?
Right.
AI slow-mo eliminates that, creating incredibly cinematic slow-motion effects.
Wow.
And if you ever need to increase the size of an image, AI Super Res does it in a way that preserves detail.
Okay.
So you're not just stretching pixels.
We've gone from realistic lighting and reflections to AI image editing on the fly. Turing truly is a jack of all trades. But it can't do all that without data.
It can't.
And lots of it, right?
That's right.
So what's the high-octane fuel line for a GPU like Turing?
That's where GDDR6 memory comes in. Think of it as the next generation of data highways, much faster and more efficient than anything that came before.
Faster data highways. Got it. So basically, GDDR6 memory ensures all those amazing Turing features have the data they need right when they need it.
Exactly, and to push that efficiency even further, Turing also boasts a larger L2 cache.
Okay, hold on. Remind me what cache is again. Is it like the GPU's RAM?
It's more like its short-term memory. Think of it this way. When you're working on a project, you probably keep the most important tools and materials close at hand, right?
So you don't have to go searching for them every time.
Exactly. A larger L2 cache means the GPU can keep more of the data it's using frequently close by, speeding up processing even more. And this is especially important for demanding applications, like, say, virtual reality.
Oh yeah, VR. We haven't even touched on that yet. It's got regular games cranked up to 11. How does Turing handle the pressure?
Well, for starters, it has this incredible feature called multi-view rendering, or MVR. Imagine having multiple cameras pointed at the same scene, each capturing a slightly different viewpoint. That's essentially what MVR does.
Multiple viewpoints at the same time. My brain hurts just trying to picture it. Why is that so important for VR, though?
Because in VR, you're not just looking at a screen. You're immersed in a 3D environment, free to look around in any direction. MVR allows the GPU to render those different viewpoints simultaneously, so the world responds realistically to your every head movement. It's what creates that feeling of truly being present in the virtual space.
Oh, okay, that makes sense. It's like the difference between watching a football game on TV and actually being in the stadium.
Oh,
right?
exactly. You're not just observing the scene, you're a part of it. And to make those VR experiences even smoother, Turing uses a clever technique called foveated rendering.
Foveated rendering, another new term. Break it down for me.
Have you ever noticed that you only see sharp detail in a small area right in the center of your vision? Your peripheral vision is much blurrier.
Yeah, actually, now that you mention it.
Well, foveated rendering takes advantage of that by rendering the center of the scene in high detail where your eyes are focused, and then decreasing the detail in the periphery.
So it's like the GPU is focusing its efforts where it matters most, just like our eyes. That's incredibly efficient.
It is. It's all about tricking your brain into thinking the entire scene is rendered in high detail, when in reality the GPU is strategically allocating its resources to deliver the best possible experience.
Okay, I'm officially blown away. We've covered so much ground today, from souped-up SMs to AI coprocessors, and even mind-bending VR tech. It's clear that Turing wasn't just an upgrade, it was a complete revolution in computer graphics.
Couldn't have said it better myself. NVIDIA set out to create an architecture that could handle the most demanding games and applications, and they absolutely delivered. And the really exciting part is we're only just beginning to see what Turing is capable of.
Speaking of pushing the limits, remember those RT cores? The
Right.
ones that made ray tracing possible in real time? Well, the white paper hints that they could be used for even more than just visuals.
Absolutely. NVIDIA mentions things like audio simulations and physics calculations.
Wow.
Imagine a game where sound travels realistically around corners and through objects, creating these incredibly immersive soundscapes.
That's what?
Or even games where the physics of objects are simulated with unprecedented accuracy, all thanks to the power of ray tracing.
It's like they unlocked a whole new dimension of possibilities, and the white paper itself is just the tip of the iceberg. Who knows what incredible applications developers will come up with as they continue to explore Turing's potential.
That's the beauty of it all. Turing set a new standard, and it's going to be exciting to see how developers, researchers, and creators push those boundaries even further.
Well said. And on that note, we'll leave you to ponder the possibilities. Until next time, keep those minds curious.